Hi, everyone. Thanks for coming. And yes, Monica already said, let me repeat just that there are notes. I updated them, so they include the materials of what we will be discussing today. So please check them. Yeah, I also see many experts in the audience, so I hope they will help to clarify some of the questions as they emerge, because today we will be discussing things where many questions can emerge. My first lecture was last Friday, so I assume everyone has already forgot everything that's been said there, more or less. So let me just do 1 minute reminder. We consider the process of scattering, and we think about it. Well, here I draw the massless scattering, doesn't matter. We would like to characterize it, but we do not discuss how to compute this process in some particular theory, but rather we're discussing the general properties and the tools to characterize it, and then maybe bootstrap it, which is to constrain our ignorance further. The three main things which we would like to use to do this are unitarity, analyticity, and crossing. And let me just say that, because if you haven't never worked on the subject, it might sound these are just some abstract words which do not translate into some particular computational power. But you should really think of this as like, you're given a Lagrangian, you can do some computation. So if you're doing that much of analyticity, or that much of unitarity, or that much of crossing, that affects your power to compute. So these are really concrete things which you can exploit. And the more analyticity you have, the more powerful you are. The more crossing you have, the more computationally powerful you are. So, and finally, we would like, as we discussed with some of you during the lunch, in principle, these are very general things. We can add here some extra data which puts puts in some life into this very general program. And extra data could be either something that you measured in the experiment, something that you know from the lattice computation. It could be symmetries in gravitational theories. These are asymptotic symmetries, etc., etc. So these are things which we know, and we can always put them in. And these are things which will help us to constrain what we do not know. That's the basic idea. And then it's up to you how to combine these ingredients, how powerful you are, etc., etc. So that was the recap of lecture 1. Now, if you remember that this is at the end of the lecture 1, we said that the states, the Hilbert space will be just a set of asymptotic states, which are multi-particle states, and there is an operator S matrix, which describes the transitions from the in states to the out states, and it encodes everything that happens in a space-time. So space-time is emergent in this picture. And the goal of today's lecture is the following. First, I will review the basic kinematics. This would be a bit boring, but hopefully brief. And we will discuss the unitarity, analyticity, and crossing. So our first approximation to it, when we'll discuss it further. And my final goal, I don't know if I will manage to do it today, but would be to prove, so that you can follow the derivation step by step in a very detailed way, to prove the so-called the Froissart-Martin bound. This is probably the most famous result in the S matrix theory. On the total growth of the cross-section. So if you say collide protons at LHC, how quickly at asymptotically large, and in fact at finite energies also, how quickly the total cross-section can grow. That's my plan. Okay, so to start with, let me describe again. Remind you with the formula. My first formula is that we have the operator S metric, which maps which allows us to compute maps in states to out states, which are given by S in, and then we consider, and then it's unitary, and we can study now the transitions between some, say, in and out states, which are computed in the space of square integrable wave functions in a space of on-shell momenta. Because recall that these states are characterized by some particles, so you have some wave function out, say wave function in, and then this operator S matrix evaluated in some set of m and n particle states. So this is, say, m particle, this is n particle. It defines some kernel, which also depends on the momenta, and which we would like to study. So it's everything here depends on the on-shell momenta. These measures I wrote last time. These are just simple measures in the space of on-shell momenta. So we would like to understand what are the properties of these kernels, and let me start with one first property of this kernel, which is known as a clustering, which is a statement that we just encode the statement that if you take a bunch of wave packets, say here, and collide them here, and you do them in the next galaxy, these two processes do not depend on each other, and this is encoded in this property of the S matrix, where we can write it as a so-called connected S matrix plus sum over permutations, and here we have products over connected S matrices, where you split your m ingoing particles or n-going particles into arbitrary number of groups, and then for each group you can separate them. So whenever you can separate them, you can have a connected S matrix, and this property is called a cluster property. So the symbol, so this is a clustering, and to really characterize this connectedness, again, this is something very intuitive in coordinate space. Now I'm writing it in momentum space, and this label C translates into the fact that these kernels, they're proportional to the momentum conservation. So since we are scattering particles in Minkowski space, we have some m ingoing particles and outgoing particles, their momenta has to be the same. And here, this delta function is simply momentum conservation. And here, let me call it T function. So this is what multiplies this delta function. So this is a structure of the scattering matrix, which encodes clustering. And of course, this is all very kinematical. All the dynamics will be in this T functions. So the first property, which encodes stability of particles, say stability of asymptotic states, is that if you take connected guy, say 1, and transition to any k larger than 2, this is 0. So this just tells you that if you have one particle, this will forever stay one particle. So the transition from one particle to any numbers larger than 2 is 0. And for asymptotic states, we only consider stable particles, because if it's unstable, it decays and is not presented far away. Now in Minkowski space. Sorry, I forgot again about the line. And so the simplest S matrix that we can consider is a connected transition from 1 to 1. And this S matrix is completely fixed by symmetries. And it's given by the following expression. which is also known, I guess, as a commutation relation of just free of oscillator modes in the free field. So this is just a simple propagation of a particle, free particle through space. Now this is not what we want to study. This is too trivial. So what we want to study instead is yes, and let me remind you that just if you forgot, that if you have a free field, so if you have a AP, A dagger Q, the commutator of two modes, this is exactly this thing. It's T minus 1, P0, which is this if the particle is on shell, and the momentum conservation. So in these lectures or in these talks, I'm focused on the first non-trivial process, which is not one-to-one, but instead it's 2-to-2. That's our basic interesting process. So it depends on, say, outgoing momenta P3, P4, P1, P2. And first, looking at this formula, well, the simplest subsets of two particles are one particle, and one particle S matrix is completely fixed. So we have a product of S11, C, say, for example, it can be P3, P1, SC11, P4, P2, plus we can have permutation, so P1 going to P4 and P2 going to P3. So it's the same. I will not write it. No, sorry, let me write it for the following simple reason, because this S matrix is very special in our study of S matrix theory, because this is the only non-perturbative S matrix which we know exactly in high dimensions. So if, say, in 2 dimensions we have some integrable theories and some specific S matrices, in high dimensions the only solvable theory is a free theory, and this describes just non-interacting particles propagating through empty space. Now, in any interacting theory, of course, when we have some 2 particles coming in and going out, they will interact. And this corresponds to the fact that we have this here S22C, this connected scattering, and this S22C is proportional to P3 plus P4 minus P1 minus P2. And we get here the our central objects that we will study for the rest of the time. It's a scattering amplitude. And in fact, sometimes when we say scattering amplitudes, we skip all the steps because they're trivial and they're kinematical, and we immediately talk about this object.
Sorry, Sasha. So about your the fact you chose to ignore 1 to 2, say.
It's just saying that the particle is stable.
So for example, if I have some particle that's emitting a photon.
So, well, then if you have a process 1 to 2, then say for the case of a massive particle, if you have an on-shell particle just at rest, it will not emit a photon, right? You have to have some kick or something. Just electron at rest will stay at rest forever. It could be that you're right. It could be that if you say have a particles which say propagate far away and they're charged, and then there is some Coulomb field between them, and so they continue emitting photons. So it doesn't really make sense to talk about a completely isolated particle. And this is a source of the infrared divergences, that you have to modify the Hamiltonian. But here we're saying that the far away the Hamiltonian is just a free field, effectively, and for the one particle, it just stays forever. This is what we call an asymptotic state, and in a sense, this is my starting assumption of the whole
I see. So basically, you're excluding everything where you might have some non-trivial asymptotic interactions. So
yes.
Is this the answer to?
Yes, the idea is that far away interaction is turned on, and it makes sense to talk about just free particles. Guess it's not obvious, but it's reasonable.
Your scattering matrix 1 to 1, the delta function is d minus 1. Those are vectors, I mean.
Absolutely. Okay.
Sasha, can I also ask a quick question?
Please.
So are you saying that one does not need to start with 2 to 3 to make contact with BMS, but already 1 to 2 would see some structure of these asymptotic symmetries?
No, I'm not. I would say to study the asymptotic symmetries, it will connect 2 to 3 to 2 to 2. I do not think you have any non-trivial, because 1 to 2 is just 0. So you study instead, if you have 2 to 2, then you can discuss soft theorems. Of course, if you have, again, if you have, say, a graviton, which can then collinearly split into two gravitons, then maybe you have to worry that indeed 1 to 2 is not 0 because it's because of some collinear effects of massless particles. But at least in gap theories, it's true. And I think in higher dimensions, when there are no infrared divergences, when we talk about if we believe in asymptotic completeness, then this is what we assume. So I don't think there is any non-trivial soft theorem at the level of 1 to 2 where there is an on-shell graviton propagating, at least not that I know of. Because if you want to have an on-shell process 1 to 2, then you need one of the particles either to be off-shell, or you want the particles to be collinear. And if the particles are exactly collinear, well, it's a bit of a singular configuration. So here, first of all, when we will talk about complex kinematics, and this will be part of analyticity. But here, because we are really talking about particles, Hilbert space, unitarity, we are talking about real kinematics. So all momenta are real. They're just, really parameterized physical particles. And then we will find that, okay, we can try to continue our theory maybe to some different signatures. We will do all the time of considering these functions to be some analytic functions, then sure. But at this point, everything is real, and this is the non-perturbative structure of the S matrix.
Should we? Are you restricting your space of theories because of this asymptotic, not asymptotic freedom, but you understand what I mean, of the Hilbert space? So, so will you ever be considering, I don't know, gluons and?
Well, say in D larger than 4, my guess would be no. It's not restricted. I'm not restricting myself.
But in D equal to 4, we shouldn't be thinking.
In D equal 4, it's more complicated because the asymptotic Hamiltonian will not be free exactly. So we have this many separated particles, but we have to solve the asymptotic dynamics together with a bit of interaction. So
I'm just asking. So should I just assume that what you will be saying in the next for the rest of the lecture simply doesn't apply to 4D? I don't know.
Yeah, to 4D this does not apply because it's just all the objects that I write, they do not make sense in 4D. Well, so there is no, okay.
No, because Monica mentioned gluons. Monica, why are you mentioning gluons here? I'm sorry, give me the mic so you cannot respond. But there's no S matrix for gluons, right?
For gluons, for gluons. You probably meant particles. You probably meant particles which make it to asymptotic. So not gluons, but photons or gravitons. I think that's what Monica had in mind.
but it will apply to scattering of asymptotic states in QCD, say, with
Oh yes, but yes, of course.
Yeah.
So this is our main object, and it's a function of Lorentz so-called Mandelstam invariants, which are defined as follows. And here somehow I choose the signature, which I want to change now, but maybe it's too late. So let me write this once so that you have it. It's the definition of Mandelstam invariants. And also, if you imagine that you have a scattering of two particles, say 1, 2, and 3, 4, in some center of mass plane, some angle, then you can write these expressions as 4m squared plus k squared, where k is the momentum of these guys in the center of mass frame. So the total momentum in the center of mass is 0. And here, so you have cos theta minus 1. And here you have 2k squared minus 1 minus cos theta. And these guys, they satisfy s plus t plus u equal to 4m squared. And the cosine theta is equal to 1 plus 2t s minus 4m squared. And one thing that you want maybe to remember, that the dimensionality of this object. So when we talk about the scattering amplitudes, it's m 4 minus d. So in 4 dimensions, this is dimensionless. In high d, it will be 1 over mass. In 3d, it's mass. And the punchline here is that, okay, s and t are some relativistic invariants, but the scattering amplitudes that we are talking about, it depends on two things. And two things are energy and an angle. So these are our two variables. Now, there are three different, so sometimes you can see what's known as a Mandelstam plane. So let me quickly draw it. Take three vectors, which are all pi over 3 apart. Let me call the unit vectors s, t, and u. And you can check that, say, if they're all unit length and pi over 3 apart, then they sum up to 0. So now if you take any vector, say vector x, and you define a scalar s to be x dot s, and t to be x dot t, and u to be x dot u, of course, you will get that these three numbers always sum up to 0. That's by construction. And so that's what Mandelstam plane does. It's a way to depict this kinematics where s, t, and u sum up to 4m squared. So what we do is that we take this triangle, and so we can embed it into so this every point on this plane specifies a point that satisfies kinematics, and say this is s direction, and this point is 4m squared, and this is 0. So let me switch u and t. So this is a t direction, therefore this is t equals 0, 4m squared, and this is u direction, if you have never seen that. And again, this is will be 4m squared and 0. Now, as you see, if we look at this expression, so here I wrote this expression in what is called an S-channel kinematics. So particles 1 and 2 collide and produce 3 and 4. If you look at this expression, you see that, say, here, for any momenta, S is larger than 4m squared. Therefore, if you want to describe the S-channel scattering, you cover only this region. So this is S, because you see here for any angle, cosine theta, both t and u are negative. Cosine minus 1 minus cosine. So the negative is 0. So physical value of parameters, which describes scattering, is not covering this complete plane, but it covers 3 regions. And as I already said, say this S-channel, it describes process where 1, 2 goes to 3, 4. There is another region here which describes process 1, 3 goes to 2, 4, and this is a T-channel. And this is a U-channel. Which describes 1, 4 to 2, 3. So if you are an experimentalist and if you really do the experiment, you cannot access this. You can only access these regions. But as we proceed, of course, what will happen is that this S and T will become complex, and we will be discussing this scattering amplitude in the complex plane. However, the basic kinematics is this. Now, next thing I want to discuss, it's also a bit kinematical, but I will be making comments along the way, which hopefully will become slowly more and more interesting. The next thing I want to discuss, what are the implications of unitarity for this object? So this is one of these words. So this is what we will discuss now. Okay, we can write the expression for the S matrix, which will be relevant for me. Here is a 1, which is exactly this expression which describes no scattering. It's a free field theory S matrix, plus I operator T, where operator T describes this connected scattering. And we now consider this matrix element between 2 particle states of this T operator. And as I wrote already, this is given by that expression, so it will be a delta function and whatever. Now, what we want to do, is we want to see what does it mean for this S matrix to be unitary when we apply it to the 2 particle states. So what we want to do is we want to take this equation, then we want to add to it a unitarity equation, and we would like to sandwich it between 2 particle states. And as we do that, we do the following thing. So we say P3, P4, S dagger, P1, P2 is equal to the same, just 1. as you do that, and maybe I will skip this detailed steps, you can well, it's a trivial algebra, but you see that if you plug this into this equation, what happens is that 1 cancels. So you have 1 times 1 dagger, it's 1, cancels this 1, and what's left is just t. So unitarity equation only relates the interacting part of the S matrix, and it takes the following form. This is what you get from this guy. And then, of course, you have a term, and this is equal to P3, P4, T dagger, P1, P2. And now as the next step to turn that, what we do is that we insert here the complete resolution of the identity. So we insert the complete basis of states. And we get our formula, which expresses non-perturbative unitarity, which takes the following form, that this is equal sum from n to infinity d mu n p3 p4 t. Here we have n particle state. And here we have the same particle state, T dagger, P2, P1. Now, the first thing about this equation that you see is that the right-hand side has a nested structure. And if your theory is gapped, there is this hierarchical structure on the right-hand side, which in fact then turns through reshuffling of all these principles again and again. This hierarchy manifests itself. And the hierarchical structure is the following, that if you want to have a process where you, say, produce n particles, you need enough energy. So if we go to this variable s, which describes the total energy of the process, if you have, say, this s between 4m square and 9m square, you only have n equals 2 in this term, because you just do not have enough energy to produce more than 2 particles. If you have, say, s between 9m square and 16, then you can produce 2 and 3, etc. Okay, so just keep this in mind, that already at this stage, imagine you would like to implement this on the computer or something. There is this hierarchical structure, and which is part of what we mean by this gap theory. Now, here comes where this was all something that we can discuss and really measure all these curves and plot them as cross sections. Now, the starting point of the S matrix magic is the following. The starting point is observation is that, as someone asked already, that we should not restrict ourselves to S and T being real and just living in these physical regions. We should in fact think of the S matrix as of this function, this physical functions that we try to study and observe, as a boundary value of some analytic function where, say, S was positive. Sorry, S was complex. And so this is something that is known as a, well, let me call it a epsilon prescription, but this fact is really the starting point of everything, because and to understand that, well, last time we discussed the signal model, and we saw that the fact that this is true was closely related to causality and having a local space-time, having relativistic theory. People derived it, I guess, using, at least for 2 to 2. This is a non-obvious statement, and for 2 to 2, this has been shown in many ways, I guess, starting from QFT axioms, starting from axioms of macro-causality, etc., etc. It's true in perturbation theory. So I'll just say that this is really the fundamental fact about S metrics, and as long as we departed from this tiny corner of real kinematics, we now will start explore. As soon as you say, okay, there is some analytic function which lives in a complex space where S is complex, then many questions arise. For example, what is the analytic structure? What is the structure of singularities of this function? And this is really at the core of analyticity, which is it's just an attempt to answer precisely this question. If we think of the scattering amplitude, physical scattering amplitude, as a boundary value of some analytic functions, what are the analytic properties of this function? Now, to this equation by itself is a bit, it's not yet very useful. For the following reasons is that we have here this operator T and T dagger. It would be good to, as a next step, to take this equation and get rid of all the daggers and just talk about T and matrix elements of T. And so to do this, let me consider the following thing is that, and here the way I chose to present it is maybe not the most general one, but let's say we take this matrix elements of a dagger. And if you take the matrix element of a dagger, you can rewrite it like this. So yeah, we will slowly make this formula look even better than it is. So this is a complex conjugate of this transition. So this is just a definition of complex conjugation. And then if you have a so let me consider this point, say scattering of and I will be mostly talking about scattering of identical particles. Then there is if you have a kinematics of this type, which depends only on Lorentzian invariance, you can simply see that this, if you have this matrix elements of 3, 4 to going to 1, 2, it's nothing but you can act on it with the rotation, and this is the same as you can flip the ingoing and outgoing states, and this is what we get. So again, if you compute this scattering process, well, you will see that these matrix elements are exactly the same, just because S and T will be exactly the same. Now we see that therefore this T dagger computes a complex conjugate of the same amplitude of the same object. And if you try to do something which is not a priori obvious, which is that let's take this analytic function, and I told you that these objects are present for the right-hand side of unitarity is present only for S, which is physical. So let me try to take this equation and continue it for S less than 4m squared. And so if physically you cannot do that, but in the lab it doesn't make sense to consider S less than 4m squared. But if I take this equation and try to consider S less than 4m squared, then the right-hand side is 0, and then it looks like if you do that, we see that the amplitude of S and T and its complex conjugate are real. So it's here there is this plus I epsilon, of course, that we started as. So the amplitude would be real for, say, S less than 4m squared. And this and as soon as it's real, and you know that it's an analytic function which is real on some axis, then you can define its analytic continuation. If you have I guess it's called the Schwarz principle. But if you have a analytic function in upper half plane and then it's real on the real axis, you can continue it in the lower half plane using the following equation. And you see that if you take S to be real, you just recover this equation. But then if you take S into an upper half plane, this defines you analytic continuation in the lower half plane. And so this equation, which in fact I haven't, well, it's almost usually taken as an assumption, but I guess there are claims that you can, well, there are definitely claims that you can prove it non-perturbatively, but I don't know very good. T is real, yeah. So then people sometimes also write these equations for both S and T complex, but here the way I motivated, then T is real. So yeah, this is so yeah. Well, here I'm talking about yes. Here I'm talking a physical matrix element, and for physical matrix element, if you remember, in the S channel, T was negative. So that was, yeah. So now yes, this I cannot explain much more. It's just a formal. I'm saying that the formal, in some sense, it's something. I'm saying something trivial, which is that if I think of some analytic function and then I land on some unitarity equations, I see that to have some non-trivial contribution, then S to write something like this, I need S to be larger than 4m squared. And here I'm just saying, okay, well, one natural thing to do is that when S is less than 4m squared, then you just do not have energy to produce anything, and so the right-hand side is just 0. Now, yes, well, we derive this equation using, that's the thing, we derive this equation using unitarity, right? Unitarity makes sense only for the physical value of momenta. And so this equation, let me emphasize that for this equation, I take S first to be, say, real, T to be negative. So this is where this equation has been written. Now, okay, you're saying I'm cheating. I think yes. In fact, you can say it, and so I can say that this equation it is a consistent way to think about this. So let's say if I try to think now of analytic function, I go and I think of T as a Wien boundary value, and I go for S less than 4m squared. The right-hand side is consistently set to 0 for less than 4m squared. Let me set it to 0, then I get that it's real, and then I naturally can define analytic continuation. Now, in fact, first of all, in general, it's not even correct. So if you have anomalous threshold, you will have the cut which goes below that. And then you can try to make sense of this equation. This equation will be correct for identical particles which are the lightest. However, say in perturbation theory, if you go below this cut, there is a way to think about analytically continued unitarity for this anomalous threshold, and then if you continue further where you do not have enough energy to produce anything, still you recover these equations. Now,
Sasha, isn't this a choice, in fact? So you have your function T of ST,
Yeah.
it was satisfying for s larger than 4m squared. It was satisfying this equation. Is it working? Now you have to analytically continue to the upper half plane.
Yes.
I think unless isn't this up to you to say that out of infinitely many analytic continuations which exist, you choose one which is real for s smaller than 4m squared? Because you know, we know that if you have to analytically continue function to the upper half plane from the real axis, and if you only fix values on a part of the real axis, the analytic continuation in general is not unique. So you seem to be saying that there exists one analytic continuation which satisfies this condition that it's real below 4m squared.
Yeah. So yes, there is this. What make me reluctant to agree with you, which is there are claims in the literature that this has been proven non-perturbatively.
So those claims.
I haven't really understood these claims. So maybe they make some extra assumptions.
Okay.
Or not. It's true in perturbation theory. So.
No, but then how these claims can work? It means that they have another way to define this T of ST for complex
Yes,
SNT,
yes. So
which is not appealing to this equation, but appealing to some other formulas which automatically provide T of ST which satisfies this equation. Yes. So it must be something like that.
Something like that. So I think what is done, at least something, some arguments, the spirit of the arguments that I've seen, people study, say, 4-to-4 scattering, and then try to define this 2-to-2 amplitude and then physical region as some object which appears inside 4-to-4. But at this point, I really don't have a good. I'm sure there is a better way to go over this spot, but we can call it choice. I can motivate it in this or that way. But in all the cases that we know of, say, and then definitely in perturbation theory, this is what happens, and so I will definitely assume that. Now, well, after you've done that, what happens is the following thing, and that's where the equation becomes nicer, is that we see now that to discuss these daggers, and if we take this analytic continuation into the upper half plane with I epsilon prescription, then taking a dagger, it's the same as approaching this S not from above but from below. And therefore, what this guy does here, it computes for us what is, let me define it, discontinuity in S, which is defined like that. And here I write it like this. So what does it mean? Is that to compute this difference, we take the difference, we imagine some analytic function, and there is a cut starting with 4m squared, and then you either approach from above or approach from below. And this is nothing but taking the discontinuity. So on one hand, we have on the left-hand side of the unitarity equation, we have a discontinuity. And on the right-hand side, we have the same. We have the product of two amplitudes. So here, let me write some kernel of some momenta. Let me write this equation precisely. So what you get is, here I put 1/2 because my particles are, I consider identical particles, so it's a bosonic, it's a Bose factor 1/2. Then I write the invariant relativistic volume, and here we have delta function for momentum conservation, and we have T plus for say if we have a 2 to 2 amplitude, T minus, and we have some multi-particle contributions here. So here what I did is that I just unpacked a bit this equation for n equals 2. So this is what explicitly it means. You have sum over complete two-particle states. You have two different branches of the amplitude. Again, T plus coming, meaning that you approach S from above, minus from below. And there are multi-particle states. So this is the first.
I'm sorry, by multi-particle mean n larger than 2?
Yeah. Multi-particle is n larger than 2. Now, there is a way to rewrite this equation more nicely, in the sense that, well, these two functions and depend again also on S and T, and you can go over this kernel and rewrite it in terms of S and T. But maybe what I will do is that I'll skip this part because it's in the notes and it's pure algebra. So please check them. You can just massage this and rewrite everything in terms of S and T. But the point is that we have an equation which relates discontinuity of the amplitude to itself in plus multi-particle contributions. If you restrict energy to, say, less than m squared, then multi-particle contribution are not there, and we have a nice equation, non-perturbative nonlinear equation satisfied by the amplitude. And here there is a big difference between theories with massless particles and theories with massive particles, because in theories with massive particles, you have this hierarchical structure, but say in gravity, because gravitons have mass equal to 0, all the unitarity equations come at once. So this is, I would say, one of the, from the point of view of this non-perturbative bootstrap, at least in d larger than 4, this is one of the biggest differences, in fact. Otherwise, all the equations are effectively the same. And talking about gravity or not talking about gravity is very similar. But this hierarchical structure is lost. Now, let me just say that if you consider in this equation t equals 0, then the outgoing state and the ingoing state are the same, because it corresponds to scattering on over 0 angles. And in this case, you can check that what we are doing here, we are studying something like psi t dagger psi in the right-hand side. So all this right-hand side is just psi t dagger psi, and therefore it is non-negative. So for t equals 0, the equation is that 2ts S0, it's larger or equal than the same thing, and without multi-particles. So you have to impose it, just the same thing here. And that's it, because multi-particles will produce something which is non-negative. So you can write it like that. If you drop multi-particles, you get larger equal. Now, let me also define, since we are going slowly, but and not even steadily, to the for us R bound, let me define what is called a cross-section. And total cross-section, and physically, because you want to define the probability, say you start with 2 particles, and you just produce whatever you want, and you want to know how much you can produce. Well, and that's exactly the idea we discussed there. If you set t to 0, effectively you can glue it, and then this is what this describes. So the physical meaning of this is simply the probability to produce, total probability to produce as many particles as you want. And so the convention is that this Ts of S and 0 is S minus 4n squared sigma total. And so this is a definition of a total cross-section, and well, it is a cross-section because it has the dimensionality of an area. So the Froissart-Martin bound, it will be the bound on this quantity. Now to proceed, we will next we will introduce partial wave expansion, which would be the way to go from this kernel. So it will be a way to diagonalize this kernel, essentially. And the way we do that is the following. So let me next introduce the partial wave expansion. Again, maybe I will not spend too much time because it's explained in many places, but the idea is that instead of talking about n particle states as your intermediate states, you go to the basis of states with some total momentum, some total form momentum or d momentum, total angular momentum, and then some projection of the angular momentum. And what you find is that because the angular momentum is conserved during the scattering because of rotation symmetry of the problem, then if you start with a state of momentum g, some certain angular momentum g, and you go through the scattering, you get only the states with this angular momentum contribute. And effectively, if you do this exercise, well, you have to understand this sort of overlaps. If you start with a 2-particle state and you compute this matrix elements, and then you compute the overlaps of the matrix T, what you end up getting is the expansion of the amplitude in terms of what is known as partial wave coefficients, and it takes the following form. It's a sum over all angular momenta, nj of d. It's just some numerical coefficients which you can find in the notes. This is partial wave coefficients, and here you have a Geigen-Bauer polynomials. Again, all the normalizations in the notes. In 4 dimensions, these are Legendre polynomials. In high dimensions, these are Geigen-Bauer polynomials, and these guys are called partial wave coefficients. If you want to define this Pj, it's natural to define it by thinking about, I guess, Casimir equations for the total angular momentum of particles P1 and P2. And if you do that, you derive some differential equation that satisfies, it's satisfied, and then you can derive it, but okay, I've done it for you. And the basic point is that, and of course, well, they form, they're all orthogonals for different j. So in practice, this fj is defined by simply taking the amplitude and projecting it, integrating it against one of the pj's, and in this way you get the partial wave. So you get, I'm introducing some notations for numbers. These are some coefficients, but I do not write them because they are written in the notes, and they are not important for us at the moment. So you have integral from -1 to 1. This is integral over angles, and now what happens is that note that I told you that the amplitude is a function of energy and the angle, and here we integrate over angles, so we get these partial waves. Now, as I told you, the idea to do that was because unitarity will simplify, and indeed you can check that if you take this expansion and plug this in this formula, unitarity becomes the following statement. So imaginary part of this partial wave is well, large as equal 4 minus s minus 4n squared d minus 3 over 2 square root of s, absolute value fj of s. So what happens is that you project to the partial wave j. This gives the same as imaginary part of f of j, and fj and fj bar come from these two equations, from this t, and because it's diagonal in j, you get only a single j that survives. Now, this larger or equal arises simply because this is a contribution of 2 to 2 to unitarity, but there is a contribution of multi-particle guy. But in this way of doing things, its contribution is non-negative, and therefore, if you drop it, instead of the equality, you get larger than equal. And finally, if your theory is gapped, and you restrict your energy, say, between, for example, 9m squared and 4m squared, you do not have any multi-particle channels because you don't have enough energy, and then the equation becomes simply that they're equal. Again, this is the equation which does not exist in a massless theories, because if we consider scattering of gravitons, we always have for any energies larger or equal, because mass is 0, we cannot separate them. Also, this equation, for example, does not exist in a CFT bootstrap, for example. So this type of equations are really specific for the S matrix scattering. And you can write this equation in a more intuitive way if you introduce this SJFS, and this is, you can think as a sort of complete scattering or in the J, in angular momentum J channel, where one comes from the disconnected piece, and f of j describes interaction. So if you have a free theory, Sj of s is 1, and fj describes scattering. So 1 comes from the projection of the non-interacting S matrix, again on this angular momentum eigenstates. Now, then unitarity becomes very simple and very powerful. Oh, it is powerful. And it says that in the elastic region it's equal to 1. This is this. And then inelastic region, let's say equals in 1. So that's it. That's what unitarity is, and that's how we will use it in the rest of the lecture. So I'm at this point done with unitarity. And next, let me before we have a break, quickly discuss. I'll take a few more minutes and discuss impact parameter representation. So you can ask, okay, what it's just good to have in mind, because sometimes when we think about scattering of things, it is much more intuitive to not to scatter them in an angular momentum basis or into momentum basis, but it's much more intuitive to imagine two-wave packets separated by distance b and in some transverse plane, because then you imagine, okay, when b becomes large, then things should not interact. Well, if they exchange particles, there is a Yukawa potential, etc., etc. So it's very useful when you talk about scattering to relate to this physical picture, because we have a lot of intuition about that. So how do you go from this picture to the impact parameter space? You do it in the following way. So the claim is, if you take this formula, TST, the expansion in J, NJD, Fj of S, and Pj angle. And now you take in this formula the following limit. You take S to infinity, you take J to infinity, and you fix B to be 2J square root of S. Now, the basic idea is that, okay, this is here, this is a definition. And I will see now how it is related to this picture. And what is the precise relation to this picture? And the way it works is the following. Okay, a priori, if you haven't thought about this problem, it looks like a random thing to do, because, okay, well, why would such limit exist? But then we'll, if after we now discuss this limit, we will find that what it does, it describes a scattering, and this partial waves becomes the phase shift at some impact parameter. So this limit, in fact, should exist because we believe that this picture makes sense. So we should be able to discuss, to isolate objects at finite fixed impact parameters. And in this way, we get this phase shift. Now, what happens in practice if you try to take this limit into this formula and take this limit at the level of this formula? Well, here I assume that at the level of this fjs, this is just a nice thing to do. So this becomes some object which is a function of s and b, and the rest of the factors you can rearrange them slightly, and this is done in detail in the notes. To get. So I forgot to write one formula. Let me write it right now. So if you know, one way to solve this unitarity, and this is related to this exercise, one way to solve the unitarity is to say that S of j and S is equal e to the 2I delta j of S, where the imaginary part of delta j of S is larger than 0. So you see that if S of j is pure phase, of course you satisfy this, and if the imaginary part of delta j of S is positive, it's less than 1. So let me just introduce this object delta j of S, and when delta of j, when you take this limit, what happens is that if you take limit of s to infinity, delta j equal to b square root s over 2 of s, what we get, I call a phase shift at s and b. So if you do this, if you take this definition and you take this limit, you get the famous formula.
I don't understand. What you take the limit s going to infinity and you get a function of s, so I don't understand.
Yeah, so well, you should think really that we take s to be very large and we take j to be very large. So we get some function, let's say.
Compared to what? Compared to the mass of the particle?
Compared to everything, yes. Compared to mass of the particles, compared to the coupling, it doesn't matter.
No, but that's important. It matters, in fact.
Yeah. Well, of course.
No, in fact, the reason so this transformation, so you had already undertaken one transformation to this angular momentum transformation, but that was more innocuous because it was just a change of basis of asymptotic states. Here, I have a feeling that you want to say that we shouldn't think of this impact parameter states at fixed transverse position. We cannot think of the states as asymptotic states because they will diffuse. I mean, clearly, those states are not asymptotic states. So we cannot, for example, I have a feeling that you want to say that we cannot derive this matrix in the impact parameter representation just by passing to the limit of asymptotic states in this transverse plane and then discussing everything in that basis. That would not work, really, or it's really more subtle.
The way I introduce it is the best way I know how to go from non-perturbative partial wave to something which becomes. So we can start taking the sum, and we can try to analyze what happens.
But you make a saddle point approximation.
Not really. Well, I can split this sum. I can split the sum into low spin and high spin. And by high spin, I mean, say, all the spins. Let me do it more carefully. So we can start from j equal to from 0 to j star. And this j star I can take to be square root s b over 2. Plus, I can take a sum from, well, this j star of b to infinity. Now, these guys effectively say all the spin zero guys collapse into. Sorry, I can take here some b stars, some b star fixed. I can take this tail, which involves all the low spins, and just apply to it non-perturbative unitarity, I cannot do much about it. I will always have to be very careful, and this corresponds in particular to scattering at 0 parameter, at hard scattering. And whenever we do some non-perturbative analysis, we always have to take care of the slow spins. Now, the story with the impact parameters, I mean, it's by definition, because we try to separate objects. It is a story about the tails at large spin. So in particular, we are asking what happens to the sum. What happens to the sum as we take CGA, as we take S to be large. So as we take S to be large, well, this spin becomes larger and larger. Then these spins and energies both become larger and larger. And what I'm saying is that in the physical theory, what we'll find is that these partial waves, they have a nice expansion in 1 over S. Okay, this is of course based on a physical intuition. I don't know how non-perturbatively this is the formula, and then we can just work with it. In fact, we don't have to introduce impact parameter. I just want to introduce it because it's very useful. However, okay, one way to think about it is that if we take care of the slow spins, the higher spin tail of the sum, it becomes effectively this scattering at fixed impact parameters, where the sum over the spins becomes the integral of impact parameters from some b star to infinity. These fj's of S, and in particular these guys, they just admit some limit. So again, if you take to infinity in physical theories, we will just find that there is a correction to this, which are related to 1 over j corrections. So if you wish, yes, if we want to be rigorous, then I just don't have to talk about that, and we have these equations, and that is it. Now, in practice, what happens is that these fj's of S, they're not just some abstract functions, but they, if we take this limit, they become simply scattering at describe scattering to a impact parameter. They decay exponentially. If you take the b to be large, the size of the decay is controlled by the mass of the particles that exchange. And then if you take, and moreover, if you take this limit at the level of the sum, you see that to leading order, what you get is exactly what people write in the impact parameter transform. So you get that these sums over Legenders, etc., it just becomes the transform with respect to the relative momentum. So in other words, so we take the usual way the impact parameter is introduced, at least as far as I know. We take the amplitude with some exchange momentum in the transverse space, and then because we want to separate the wave packets, we do Fourier transform with respect to this exchange momentum, right? And if we take the limit of this formula, that's precisely what we get, and this delta j of S becomes delta S of B. We have this integral. Of course, again, if we do this properly, if we do it taking care of non-perturbatively, there are these tails. The integral does not really go from minus infinity to plus infinity. It's cut off by S. But because we take S to be large, it doesn't matter. So at least if I try to make sense of this formula, the best sense I can make of it in a non-perturbative context is that there is a really well-defined formula which describes all the physics, finite impact parameter physics, zero impact parameter physics, and this formula that we write for impact parameters, it's an approximation for the large spin tails of the sums. And then indeed, if we take if we take some Yukawa potential or gravitational scattering, we always find that this formula is working. Now, the unitarity for this object, well, this object becomes, of course, just scattering phase S and B, and unitarity becomes it's less than 1. And I wanted to finish with before the break with sometimes a sloppy or maybe a little bit quick derivation of the Froissart bound. You will not be satisfied, but I think it's a good derivation to have in mind. Now, again, just let me say again, because I was quick at this point, what happened. So here we consider 2-to-2 scattering, and we imagine that the exchange momentum was some q, where this q is happening in the transverse plane. So say if we have a scattering, you can imagine that there is some transverse plane where the objects are separate, are living with some momenta, and then if we have 2 eigenstates and we want to fix their relative position, well, we do the Fourier transform with respect to the relative momentum. And this is what is done here. So that's a connection between this formula. Yeah. Thank you.
Okay. So how is B defined? This is a vector, but the definition that you gave on the left.
Sorry?
No, how is B defined? Because the
So B is defined like this. So what I do is that effectively I try to take I'm taking the large spin tail, and I parameterize this large spin tail in terms of B. So you see that
in the direction of B, because there it's a 2-dimensional integral, so it's aligned.
It's a D minus 2-dimensional integral, and if you start with this sum and you take this limit, you get D minus 2-dimensional integral. So this formula, it requires some derivation. I added it to the note, but what it does require is you take the limit of Legendre, you get the Bessel function. You see that this Bessel function arises as the integral over the transverse plane. So that's how it comes about. And yeah, and the phase shift, no action happens here. The integral, the limit just exists. So that's the thing. That this limit at the level of this partial wave, I think the claim is that if we take a partial, any non-perturbative partial wave, the function of S and J, and we take the limit, if we are powerful enough, we will find that just this limit converges to something nice, and then plus 1 over S corrections. That's what we will find. Now, I don't know how to prove it, but I think that's what physics tell us should happen always. That's what so this formula, again, I've written it, but you always should think that if such formula is written, there are corrections to it. But the idea is that 1 over S suppressed. So I would like to now prove using this formula. So for people who are online, there was a discussion about the status of impact parameter and what exactly we are doing here. And so the point of view that I'm advocating is the following, that in principle, to do computations and to discuss some bootstrap, we don't have to do that. The rigorous proofs will always rely on the formulas which are well defined. This formula, this formula, these formulas, and these formulas. So that's it. However, if you want, if the theory, if we know from the start, let's say we know from the start, it's fine. Yeah. Let's say we know from the start that it's not just some black box, but this theory admits some simple corners which are solvable. And we know that in every theory such corner exists, be it QCD or gravity or whatever. This corner is a this corner is a scattering, at large impact parameters. Now, scattering at large impact parameters, it's a not very precise idea in this ideal world of asymptotic states, because what we imagine is we prepare locally, say, 2 pions, and then we make sure that they scatter at some distance. But then we know what should happen. And what I was trying to say is that the way to implement this information, and the way this information is constantly being implemented in hundreds of papers, is by going to the impact parameter representation. And to do this at the level of the non-perturbative amplitudes is to focus on these partial waves with large S and large J. In other words, we slice the sum over J not just as some abstract sum, but we have low spins, which describes hard scattering. Now, given S, then we have this slicing with respect to this indicator. And then the idea in our minds, we connect these slices in the J space to the scattering at fixed impact parameter. Now, how make this connection completely clean and completely precise? At least I'm not fully sure. However, what we find again and again is that this connection is precise, but it's correct in the following sense, that if you come up with an argument that it's obvious that in the impact parameter space something happens, then we will find that it happens at large J. However, on the other hand, I should be maybe careful, because indeed, well, there is some limits involved and etc. But for this, we can just resort to the rigorous arguments. This is what we have discussed offline. Now I will present you a cheat proof of the Froissart bound. Well, it is what it is. And then we will derive it. Rigorously. Now, first of all, in the original paper, Froissart, he assumed what's called a Mandelstam representation. We will discuss it. This is something which has not been proven. And then what Martin did, he uplifted this proof to a proof which does not require these assumptions. Martin, excusez-moi. I am just, in fact, I think we wrote a paper last year about this large J bootstrap in S matrix, and we found that at the 60s there were three, I think, or 4 different. Well, some of them were Martins, some of them were Martins. Yes, there is André, and then there were some others, and it was very confusing because they're all A period Martin. But here, this is the André. Okay. The quick argument, let's not call it a proof, is the following. In the previous talk, I wrote the definition for the total cross-section. And now let's rewrite it in terms of this Sj of S or S of B. And again, the absolutely crucial fact for me is that in doing these operations of taking the limits, I never lost the non-perturbative unitarity. So you can check that the way we defined so far I think it's it should be -1 here. So maybe it's right. This formula looks. Now this formula looks incorrect, so I will fix it. But the correct formula is that here we have so the integral over impact parameters, and here we have sine square pi delta SB. Again, this does not quite make sense to me. So let me just write the right formula. Okay, I realize that this is not the right formula, but the right formula is this: the real part of 1 minus e to the 2I delta SB. So this is the right formula, and it comes simply from our definition of a total cross-section as the imaginary part of the amplitude. And so we take there is there is an I here, I forgot. So we set Q to 0, the exponent is gone. We take the imaginary part, which effectively, because of the I, becomes a real part. The integral over impact parameters over angles gives just the volume of a sphere, because the phase is gone at Q equals 0. And so we have this B d minus 3. Now, okay, the words you can say at this point are the following. Let's say we fixed S, and we want to understand which impact parameters contribute. Now, the intuition is that for any energy S, whatever it is, we expect that there will be a, let's say we take QCD. There will be a factor which is this, which is Yukawa potential, which simply expresses the fact that no matter how large is S, if we separate our pions into neighboring galaxies, there is always be just it will be dominated by exchange of the lightest particles, and for the pions, it will be exchange of by a pair of pions. Sorry, this factor of 2 comes from the fact that pions are pseudoscalar particles, and the pion is odd. So if you want to preserve pions parity, you have to emit 2 pions. So if you have a pion-pion scattering at large impact parameter, the leading diagram is just this. So it's pion, 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 pion. Now, okay, this is simple. Now, what do we write here? And this is, of course, the key point. And well, it's something natural to write, and then we will make it precise and we find that it's indeed correct, is that because the amplitudes were polynomially bounded, it's natural to write something like S to the n here, which simply says that effectively what it says, in some sense here we will prove, we assume what we will prove, because what it says is that the size of the object grows like logarithms of S, because, well, if we put it as the exponent, we have e to the minus b, and we have log S, and so this delta becomes 1. As S becomes larger, we need to require to take larger b, but for the log S. So at this point, you can just say that this is a model of something. It's a model of relativistic scattering, where we say that the sizes of relativistic objects, they do not grow faster than some polynomials. And then you see that, let's say we approximate this. What happens is that this integral is effectively, well, we can compute the contribution from the region where this is already very small. So at very large b, we can plug this formula here, evaluate the integral, and get something. And for the integrals from at small impact parameters, we just use unitarity, which tells us that this is less or equals than 2. So effectively, what happens is that this integral receives contributions only from 0 to B star, and this B star, we can say that it's some impact parameter where this phase becomes very small, for example, of order epsilon. So then we can trust the interaction is weak, and we can trust this formula. And then as you see that what happens here is that this B star will depends on S logarithmically, because effectively we're solving the equation we're solving, let's solve the equation Sn e to the 2 m pi b equals to 1, and so we get that b is equal n well, we can put here some n pi square to make it massless. And in this way, we say that if in this model where scattering at large impact parameter is of this type, we get that total cross section is of order n over 2 m pi log s over m pi square. There is some coefficients, of course, here, times d minus 2. So, and this is the famous bound. Now there are many wrinkles. Well, it was just a model, and here the basic point is that this has a size of some length scale. So from the point of view, if you think of some kind of black disk model, or where one pion sees the other pion as a black disk, we see that the size of this black disk does not grow faster than log s. And whenever our scattering at large impact parameter is of this type, we will always get this very universal bound. So in a sense, this bound is robust from the point of view, in the sense that doesn't matter which n do you put here as long as it's polynomial. So it really, this argument relies on the fact that at whatever, no matter how much arbitrarily large energies, if we look at the leading interactions, it will be polynomial. And it does make physical sense, because if we consider this diagram with two pions, and because when we scatter at very large impact parameters, these pions go on shell, and then we are studying the amplitude which we expect to grow polynomially. So it's very reasonable, but of course it's not a proof. And well, we had some impact parameters, and we have some assumptions, and what will happen is that and we have some constants floating around, but what will happen is that there is a rigorous proof, or at least much more rigorous proof, where everything is gone, there is no constants, but the proof is exactly of the same type, which is that we will have sum over j. Like here, we split it low spin, high spin. High spin, we use some model, and low spin, we use unitarity. So the rigorous proof of Rosser bound is exactly the same. We have low j plus high j. Here we will use unitarity, and here we will use, instead of this model, this will become analyticity. But the result will be the same as this constants fixed. Yeah, one exercise which somehow hasn't. One interesting thing about this exercise is that you see that nothing stops us from running this argument in gravity, because, well, let's take some gravitational amplitude. Let's do it in number of dimensions where there are no infrared divergences, so 5 or higher for simplicity. Well, then we do exactly the same thing. We get the low spins. We use unitarity for low spins. For high spins, we do not have analyticity in this case, but we have a model. Instead of this model, we have general relativity. So in this case, we will have low spin plus GR, and we will get a bound on the behavior of the amplitudes in quantum gravity. And this bound will not be the Froissart bound. It's a polynomial bound in that case. But again, the argument in this case is the same. And maybe here, say, for example, for comments by Slava, for this case, if we want to talk about gravitational scattering, this is the only argument we can make. Because in this case, there is no rigorous bound that we know of, but there is a we're sure there is a semi-classical limit. So we're sure that, well, in this case, at large impact parameters, we have G Newton S, B D minus 4. This is a leading phase shift, and so when this is very small, we can again cut off the sums into low spin and high spin, use this formula for high spin, which is a very conservative way, and we get an estimate for gravity. So this argument is very, I would say, very universal. We use non-perturbative unitarity for low spin, and for high spin we have to work. Yeah, that's next. I wanted to go in detail through the proof, but it requires some staging before. Okay, so next we will, as we just discussed, we will go into So next, let's discuss analyticity. Okay, so there are three big chunks of the discussions of analyticity that exist. So one is axiomatic analyticity, and this is something that we derive from QFT axioms. So this is what has been a lot of work went into this in the 60s and 70s, and I think there are a couple of really excellent references which I again put in the notes, which go through every step and give the references there, which claim comes from where. So this was one school of thought. There is a second which is related somehow to analyticity, related to unitarity. You already in the previous lecture we saw that if you write the basic unitarity, we saw that there is a bunch of cuts related to two-particle scattering starting from 4m square, because we had a discontinuity related to two particles, so 9m square. So we have etc. So clearly unitarity immediately tells us there is some analytic structure, but in fact it tells much more than that. But this analysis effectively, when you start thinking how unitarity constraints, how non-perturbative unitarity constraints analytic structure, you quickly see that asking the same questions, this question, at least with some grain of salt or grain of plausibility assumptions to make some progress, it boils down to studying of the analytic properties of Feynman graphs. Because when you study their analytic properties, you see that not the basic structure does not care that these are Feynman graphs too much. It really based on the, it's quite robust. And so there was a school that studied this, and here goes Landau equations and etc. And from here you immediately see that just for the amplitude to be consistent with unitarity, it has to have a lot of analytic structure. It should have these cuts, and there are many other singularities which we will discuss. But it's just something important to have in mind, that when you have unitarity and you combine it with analyticity, you lead into this whole world of Landau curves, normal thresholds, anomalous thresholds, many. It's a big world, and it's not fully understood. Now, here it's important that this is not completely, it's not on the same footing as this. Okay, here we believe we are on the safe grounds. Here, the logic, at least the way I see it, the logic is the following. Let's assume that the amplitude has only those singularities which are required, only those which are forced upon us by unitarity. And if you make these assumptions, then we can go ahead and we try to identify this set of sort of minimal, completely unavoidable singularities. So that's a way to think about this program. Maybe it will not complete, but I don't think there is any way we can avoid talking about these Landau equations and Landau curves, even on non-perturbative theory. So this is just important to have in mind. Even though these are Feynman graphs, it's non-perturbative business. Okay, and from all these studies and many papers, there were a couple of notions that emerged. And one important one, which I would say to summarize, for example, one with which one can read the book, The Analytic Metrics, is called, well, it's called Lightest Particle Maximal Analyticity. And this is the proposal for the maximal domain of analyticity, which is consistent with unitarity. It's consistent with everything we know from perturbation theory, and it's effectively it's the same. It's very closely related to, not exactly, but it's very closely related to what is known as a Mandelstam representation. So I think one important message here, sometimes you hear, okay, well, people back in the 60s, they found many singularities. They were very complicated. There are some complex surfaces. It's all true. However, there is a situation for which none of this has been identified. And this is the lightest particle. It may be that we haven't looked well enough, but maybe there is a more fundamental reason which would be good to understand. So this is something to have in mind. But the punchline here is that, okay, there is a proposal. At least there is a proposal. So now the proof of the Froissart bound, which is yeah.
Sorry, you mentioned that although the point 2 there is related to Feynman diagrams, it is not perturbative.
Yeah.
Is this because you're able to find these non-analyticities at all orders in perturbation theory, or there is something more fundamental?
No,
this Landau.
Yes, the reason is the following: that, well, from this point of Feynman graphs is just Feynman diagrams it's a machine, it's a gadget whose role in life is to solve unitarity. That's from this point of view. But it's not it only solves it perturbatively. However, when you draw a Feynman graph, let's say a box, what is Feynman graph? What distinguishes this Feynman graph from the full from the non-perturbative amplitudes? Well, there are propagators, there is loop integration. But let's now connect it to something non-perturbative. Let's cut it here. If we cut it here, what it does, it implements that the discontinuity of this process is equal to square of the amplitude. Well, there is a non-perturbative equation which is exactly this, and it is that, you know, the cut of a non-perturbative amplitude, it's unitarity. So now we see that if we take one discontinuity of this graph, then it encodes a cut, which is just a non-perturbative cut, but it's still perturbative because what stands on the left is not a full non-perturbative amplitude, and stand on the right is not non-perturbative amplitude. But then what you can do is that you can take this unitarity equation and continue it in the second variable. As you do that, you effectively take the second cut. And effectively what you do on the non-perturbative side, you take this unitarity kernel. Unitarity kernel, if you remember, was completely non-perturbative. It was written here. And you continue it, and as you continue it, you encounter cuts of these guys. So what you have is a diagram like this. Where each of the blobs is a non-perturbative amplitude. And in general, the double cut you cannot compute because it's a non-perturbative object. However, you see that if you ask only about the location of the cut, it doesn't really matter what you put here. It only matters where you cut it here and where this singularity starts. And this singularity starts usually at some kinematical places.
But what about non-analyticity that could be the same graph, but in which the lines that you draw are non-perturbative bound states? Would this also be captured by this reasoning?
So I start here with writing a non-perturbative unitarity equation. So it's just there. That's fine. Now, when you do the second continuation, if there is a bound state, it will contribute here, yes. So all the singularities of these graphs contribute, but as soon as you know something about analytic structure of this bound state, you just expect a singularity there. So yes, everything that's non-perturbative there will contribute. But the idea is that it's really Feynman graphs, especially their double cuts. What they do is only, if we don't care about the discontinuity, but only the fact that there is a discontinuity, is they don't care what stays here. They only care how many particles propagate here, how many particles propagate here, and this is a non-perturbative information. So that's why I think that it's important to keep in mind that when we do this, we are really just studying phase space integrals and analytic continuation of phase space integrals. It's just much simpler to study these graphs than to go through these steps. But in fact, say for this particular graph, these steps, because it's just two particles here, it's trivial to go. And this, in fact, it was done by Mandelstam, who understood that for 2 to 2. If you have more than 2, if you have something like this, 4 particles, then this becomes hard. Because then we have to understand the 4-particle phase space integral. And this hasn't been done. Well, there were some few attempts, but it hasn't been done with any systematics. But in principle, you can do the same thing. So you can start with it, continue, see where you get a pinch, and at every step, everything is on shell and this. So, yeah. Yes, and in the analytic S matrix books, for example, they study Feynman graphs, but with this picture in mind. That when we study Feynman graphs and we ask about the analytic structure, we study unitarity. And one expression of this fact is that the Landau equations, which define the surfaces, they only involve on-shell particles. There is no vertices. It's just purely on-shell. And this is a manifestation of this fact. Okay, coming back to Froissart bound, the proof relies on this, and so we have to finish. Yeah. Yes. Yeah. Like I'm happy to go a little bit. It's maybe I will. Yes. Maybe I will. We'll take 10 minutes, or is it 10, 15 minutes? Now, this is a place where you can. Yes, unfortunately, I feel quite vulnerable with this because there is a lot of work here and a lot of proofs, which I cannot say that I'm in full control of. But let me state the basic steps. In fact, I think, again, if you're a practitioner, there is a very, and let's say we just talk about scattering of lightest particles. If you're practitioners and the number of things which you want to know from here will be very, very few. But let me discuss before we go there and the derivation of the Froissart-Martin bound, and to derive it, we will need 3 steps. We will need 3 things. So first, something we discussed last time a bit is that we would like our amplitudes to be, let's say, let me take now, say, t to be negative or negative or 0. That's and that's what has been proven first, is that, again, proven using, say, Whiteman axioms, temperedness, LSZ reduction, everything you need to assume LSZ reduction, is that this amplitude is polynomially bounded. And again, depending on your level of carefulness, you can ask many questions. For example, something that we haven't discussed much, but to what extent this t of S and t is a function and not a distribution? In fact, from everything that I told you, we don't know that these are functions. These are distributions. And very carefully, if we measure a cross-section at LHC, we are measuring a tempered distribution with the averaging of a detector. We don't know that it's a function. But of course, it's a common assumption among physicists to deal with these things, that they're functions and not distributions. And then but in a non-perturbative theory, the way when you write these equations, you should upgrade it in your hand that, okay, well, this should be true on average. So the actual thing is that if you don't want to assume that this is a function, you should pair this thing with some envelope, and then on average, you should do not grow faster than S than n. Then it's, let's say you have a fixed S. For fixed S,
Are we on the real axis?
yes, we will be on the real axis. That's why. Yes, that's why it's the distribution business is important. Yeah. In upper half plane, because the amplitude is analytic, this should be fine. But on the real axis, this averaging is important. And for elastic scatter, so let me consider elastic scattering. That's what I will do. First, it has been proven that as a function of t, the amplitude as a function we have the amplitude is analytic inside the Lemon ellipse. This has been proven again as far as I know, using just QFT axioms. So you have reduction formulas, and you write 4-point functions, and you go. And so what is this Lemon ellipse? Well, it's ellipse in this. If you remember, we have cosine theta, and you have 1 plus 2t s minus 4m squared, and s is real and larger 4m squared. And then you have an ellipse with I always not sure, is it, Monica, is it foci or foci? The plural of focus. Okay.
Foci.
Foci. Okay. Anyhow, you know what I mean. Okay. Anyhow, you know what I mean, and then there is some size of it, and so the amplitude is analytic inside this ellipse. And the fundamental fact which you should know about the Lemon ellipse is the following: that as you take, so there is some size which effectively is size in T. So the fundamental fact which is only relevant for Froissart bound is that the size of, and yes, so first of all, the size of the Lemon ellipse, there is a formula, but this formula depends on the details of the theory. You can look up this formula in Eden or Sommer, the review reference I gave. It depends on the details of the theory, so it's a non-trivial formula. However, the only point which is crucial for us is that the size of this ellipse in T, as you take S to be large, it shrinks with S. So you see that, well, this ellipse becomes very small as you take S to infinity. And if you try to use analyticity in this domain, you will see that you cannot prove this Froissart bound. Sorry? The details.
I was just wondering on what kind of details can it
Yes.
depend, just on this n, on the analyticity growth?
No, it depends. It depends on the. It depends on the masses. So we have, say, we start with a 4-point function of currents, and then it depends on the external masses of particles, and it depends on the. I think the minimal mass of a particle which each of the operators creates from the vacuum. So you have LSZ reduction, where J creates a pion, and then what enters into the size of the Lemon ellipse, what is the gap above this one particle state. So it depends on a bunch of masses, and that's it. And the mass is related to what currents create from the vacuum. That's what it depends. So there is some dependence on the masses, but it's in C, but you take S to be large, it's decays. Now, the improvement of this, and that's what allowed to prove the Froissart-Martin bound, is this famous paper by André Martin about the extension of analyticity due to unitarity. So, and again, I guess I can try to go through the proof, which will take me one lecture, but the punchline is that and the improvement extension, I do not write, extension of the Lemon ellipse is that the amplitude is in fact analytic inside of the same type of ellipse, but with a t less or equals than some t0. And the crucial point about this t0 that it does not depend on s. As you take S to infinity, it's fixed. And say for the scattering of identical scalar particles, T0 is just 4m pi squared. So in this sense, it's again, it's as far as you go, because you know when t becomes larger than 4 pi squared, we start having these cuts, 2 particle cuts. And the second crucial point here is that this is based on unitarity. The proof is based on unitarity. Now, we are ready, at this point, we are ready to prove the bound rigorously. And the ingredients of the derivation is this and unitarity and this. And just from these two ingredients, we will be able to prove the Froissart bound. I wrote I think quite a detailed proof in the notes. So, but we can also, well, now I probably should stop, because the next thing I was going to do is to prove it, to derive it. But that's a natural point too. I think I will just start on Friday with the derivation of the bound, and I think it's better to do it in the morning. And also, it's since probably if everyone forgets everything else, maybe to have in mind the derivation of Froissart-Martin bound, because it's the most famous result. It's just good to have it very clean in your mind. So maybe we'll just do it on Friday.